Hey guys, welcome to another video in our series. Today we are moving on from congruence, because we've talked about it a lot at length, and we are moving on to enlargement and similar figures. Now, I've talked about similarity and similar triangles in my previous video series, so if you'd like a little bit more context, check out that from the Year 8 geometry series. But today, I'm going to once again still give you through that context as a bit of a refresher and just introduce the idea of similar figures and all the theory as well as a question, and then we'll apply this to triangles in the next video. Now think about when you enlarge something. So say you are out, you're walking somewhere, you're walking in the park and you see the photo of a flower and it's like a little bit off in the distance. Sorry, you don't see the photo of a flower, you decide to take a photo of a flower. And you see this flower in the distance, and you take a photo, and you realize, well, okay, this is, let's make this a bit smaller actually. And you're really far away from this. So you go, oh, like, I like this photo, but the flower's a little bit small. And I'm not really bothered getting up too close to it. I just want it to be more prominent. Well, what are you going to do? You're going to zoom in and you're going to take the photo with your phone. So all phones have this zoom option, and this allows you to enlarge your picture of a flower. So what you do, if this works, you get your phone out and you zoom in, you enlarge this flower. So, what's important to understand here is that the flower is still the same flower. You've taken this one and you've taken this one. Now, it's the same flower, but its size is different. So all of the little dimensions, all of the scale is the same. So for example, I don't know, this stem is relative to this bit in the middle in this bigger diagram, but the sizes are different. So all the proportions are the same, but the size is different. So we're moving on from congruence, this idea of something being completely the same, to the idea of something being very similar, similar in proportion, similar in just how it looks in general, but it has been either enlarged or shrunk down. Now this particular flower here that I've drawn, going from this to this is probably like what you'd see on your phone as like a 2x zoom. So this is like you're zooming in 2x to make this flower bigger or to appear bigger in the photo you've taken. So what that is essentially the size of the flower has been doubled. It has been multiplied by 2 here. So each particular aspect of the flower has been enlarged by what we call a factor of 2. So we can say here, each element of the flower has been enlarged by a factor of 2. Or in other words, it's been doubled. So this thing here is what we call a scale factor. So a scale factor tells us the exact degree to which, or the exact size that this has been enlarged. Gives us a feel for how big relative to the original thing has this new image gotten to. So we define this scale factor as the length or size of the image. So image length because we're going to use length because we're applying this to geometrical figures. So this guy here on the right is our image. So that's the new flower that emerges once we zoom. And the one here is our original. So to find by how much this has been enlarged, we're going to take the image length and divide it by the original length. And this is going to tell us, for example, how much bigger this is. So if we say took our flower analogy again, and this flower, for example, had a height, if we measured this length as, let's say, let's go 20 centimeters, and we zoomed in, and the new height was 40 centimeters. So we have two lengths here. If we wanted to find the scale factor, right, SF, I'm going to take the image, the new length, so that's going to be 40 centimeters, and we're going to divide that by 20 centimeters. And this is going to end up simplifying to a scale factor of 2. Because 20 goes into 40 2 times. So this has been enlarged by a factor of 2. Now you may notice I've crossed the centimeters out here. That is because I'm dividing units. So not only does my 40 and 20 cancel out, what a scale factor is, it isn't a measurement. It is just essentially how much the original has been multiplied. By what number has this been multiplied? So not only will the numbers cancel out, the units will cancel out as well. So reminder, the scale factor is not a measurement. It is just a multiplication applied to an original image, an original length or shape to get a image that is either bigger or smaller. So there's a couple of important points about the scale factor. Let's look at for what different scale factors, for what different range of scale factors we can, what's going to happen to our image. So for example, if the scale factor is between 0 and 1, so the scale factor is between 0 and 1. Well, that's going to give us a fraction, right? That's going to give us something less than a whole, something bigger than 0, but less than a whole. So that's going to be a fraction. So if we think about this through the idea of our two flowers, say the first was, I don't know, 20 centimeters, and I had another one, I created an image which was 5 centimeters. Well, our scale factor is going to equal my image, so remember, my image is the new shape or thing that comes out. So that's going to be 5 over 20, because 20 is my original one here before any changes were made. So here I'm going to end up getting, well, 1 over 4. My scale factor is in between 0 and 1. So that tells me that my new image has been scaled to be the fraction of the size of a bigger one. It's almost like a portion of the whole idea here. So what this tells me, anytime I get a fraction, something between 0 and 1 for a scale factor, that tells me that the image is smaller than the original, because it is the fraction of a size of the original here. So let's actually write down what we've noticed for this different range in the scale factors. So here, the image is smaller than the original. Okay, what if our scale factor is greater than 1? Well, we saw that in the previous example, right? The scale factor was 2. So the image was 2 times the size of the original. So the image is bigger than the original. So we've already kind of intuitively established this here. So a scale factor greater than 1 means the image is larger than the original. I'm just going to do these quotations here to show that. Now, one more case. We've looked at between 0 and 1, greater than 1. What if the scale factor was equal to 1? Well, the only way we're going to get the number 1 for a scale factor is if the size of one thing is equal to the size of another thing. Because dividing one by the other, dividing a number by the same number, gives us 1. So the only way we're going to get that is, for example, we have our flower. This is maybe 10 centimeters. We have another flower that is also 10 centimeters. Well, our scale factor is going to be 10 over 10. And from here you can pretty clearly see we're going to wind up with 1. A scale factor of 1. So it's kind of redundant because this is the exact same size here. So this is like you just taking the photo and not actually enlarging it, but just saying, oh, here, I've made an image. So the image is the exact size as the original. So the image you've taken hasn't been adjusted in any way. So if we write that in here, for a scale factor equal to 1, the image and original are identical. In other words, congruent. Because remember, we define congruence, two things being congruent, as being exactly the same in every way. So those two flowers I drew before were the same dimensions, the same height, the lengths were the same. They are congruent. They are identical. Now, let's look at one example and we will work through how we can, let's look at two examples actually, and I'll talk you guys through some of the symbols we use as well when we talk about similarity. So question 1, I have a trapezium and I'm going to copy paste this. And enlarge it by a certain amount. So I have these two trapeziums here. One, we're going to call this trapezium A, B, C, and D. Let's do it the other way around. A, B, C, and D. And I have the exact same angles here. So if you remember from the previous, not the previous video, but the previous series, we talked about if all the angles are equal, it's sufficient to say that two things are similar. It doesn't necessarily say they're congruent, but it says they are similar. So I've drawn out these two trapeziums, which are similar because all their angles are identical. So we have Q, R, S, P. And this one has a length at AB of 5 centimeters. And the other one has a length of 20 centimeters. Obviously, this is not to scale. We want to find what is the scale factor. So, first of all, we know that these two are similar because they have all of the same matching angles. So to say these are similar, the notation I use is I'm going to say my trapezium A, B, C, D. And the symbol for similarity is similar to congruence. We have these three lines once again, but they are vertical instead of horizontal. So they're vertical instead of horizontal, so that means that they're telling us something different. We're no longer talking about congruence, we are talking about similarity. And then Q, R, S, P. Here. So I've said my trapezium A, B, C, D is similar to my trapezium Q, R, S, P here. And this is what my notation tells me. So this guy here tells me this is similar. Similar to QRSP. And let's just find the scale factor so we can practice. Now, remember our scale factor is the image length over the original length and I need to just find my image length and my original length. Now we've been given two of these here. I have my 20 centimeters for my image and 5 centimeters in my original. So that gives me 20 over 5, or 20 centimeters over 5 centimeters. And remember, the units are going to cancel out because we're just looking at a scale factor, not a measurement of any sort. And 5 goes into 20 4 times. So that means our scale factor is going to be 4 here. Let's do one more example, and we're going to use a scale factor. We're going to practice this again, but we're going to use a scale factor to find lengths of unknown sides. So, for example 2, I'm going to draw an original image here. An original shape and an image shape here. Okay. My original, my image. So, let's draw in some dimensions here. So I have these two are equal, and this is y centimeters, this is 3 centimeters, this is 4 centimeters, and the image is 6 centimeters, and this one is 7.5 centimeters, and x centimeters for this one here. Okay, now I want to make some calculations. So first of all, in my part A, I want to find the scale factor. So I want to match a side from one of these, my original, to a side in my image as well. So what do I have? Well, I have two shapes. Now I'm told they're similar. So these figures are similar, that's what we're saying. And I notice they're in a different orientation. So 1 has been reflected and enlarged, if we think back to year 8 transformations and congruence. Now, this bit here, opposite the little pointy bit, is the same as this one up here. So we can find the scale factor by taking the image length. So for that side, it's 6 centimeters over 4 centimeters here. And I wind up with 6 over 4 simplifies to a scale factor of 3 over 2 or 1.5. 3 halves or 1.5. So now that we've found the scale factor, we can apply this to finding some of these unknown lengths. So here we want to find, in part B, the value of x. So this guy over here. So we want to match this to one of these shapes. So to the same bit on my original, and that's going to be this side here. So I'm going to say, well, what do I know? I know my scale factor. I'm going to use my scale factor equation. So my scale factor equals image length over my original length. And what I haven't mentioned yet, but is quite useful, I'm hoping someone's noticed, is that this is an example of an equation. The idea of a scale factor obeys an equation because we have an equals sign here. So we want to find some length on an image because x centimeters belongs to the image here. So I know that my image length is the unknown here. So I'm going to put my x where the image length lies. And my original length here is 3 centimeters. I'm going to put that here. Now, I haven't put in the centimeters yet because I know they're going to cancel out anyway, so I'm just doing this to save time. And I know my scale factor. I found this in the last question. That is 1.5. So I have 1.5 here. So my scale factor equals my image length over my original length. And I can solve this equation pretty easily because we've done this a lot in the past for equations in both year 8 and year 9. We can multiply both sides by 3. That's going to cancel my division here. It's going to undo the division, I should say. And my x equals to 4.5. And this is the image length. So this is 4.5 centimeters. Now, I've done something sneaky. I should have actually probably left these in because my x centimeters is going to be equal to 3 centimeters times 1.5, and then that gives me 4.5 centimeters because those carry over as well. Now, part C, I want to find the value of y. Now, y is on my original here. So I have to find the side on my new image that syncs up, that pretty much is the equivalent to this one on my original. And that's going to be the last one that we haven't touched yet. That's going to be my 7.5. So I'm going to set up my equation again. So my scale factor, 1.5, equals my original length, which my image length of 7.5 over my original length of y centimeters. Now, I have to rearrange this a little bit more to get y on its own. So what I'm going to do to solve this equation is I'm going to multiply both sides by y, or y centimeters, and I'm going to get 1.5 times y centimeters, because we're looking at a unit of measurement here. We're finding an original length. So we're going to keep my units, and that equals to 7.5 centimeters. And now I just want to undo the 1.5 multiplying by my y centimeters. So I'm going to divide by 1.5, and that gives me y centimeters equals 7.5 centimeters divided by 1.5. So 7.5 divided by 1.5 gives me 5. So my y, it has a length of 5 centimeters. So that is how we can use the scale factor to not only prove similarity, which we've done before, but to also take this a step further and start looking at unknown sides when given two similar figures. So that's all for today, guys. Thank you so much for watching, and I'll see you in the next video.